All right, welcome back. It's Glenn here, and I'm going to talk to you about how you prove convergence for the curved diffusion flow supported on parallel lines. Okay, let's get into it. Now, this is the second time I make this video. The first time it was corrupted again, so I'll need to fix my setup. But for now, that means that we're back to, well, I'm going to reuse the stuff that I wrote, and as long as it's still working okay, and then I will write after that if it doesn't work. Okay, so curved diffusion flow. We're going to start with curved diffusion flow because, well, the analysis is quite different between the curved diffusion flow and the elastic flow for convergence, at least the start. The start part is different, but the ending part is the same. So there's that. It was also a little bit different when we were preserving the total turning condition, but this is more different than that. And the curved diffusion flow one is shorter, so we're going to start with that. Okay, so the crux of it, well, yeah. Here's some text that I already wrote. The state of play. Let's recap. So we want to prove convergence for the curved diffusion flow. We need to make uniform the estimate on the position vector because right now it's just like this. It's bounded by an exponential factor, and that's not very useful. I mean, it's great, but it's not very useful. The second thing is that we want to have convergence to a straight line, exponentially fast even. So we really want these to go to zero. Right now they're just bounded by constants. So that's no good. I mean, it's good, but this is our task. This is the main thing we need to do. Okay. And really, the key thing is the following estimate, following claim. Okay, so we take our quantity and, well, we started off saying it was less than 2 pi over 3, actually. So why is it 2 pi over 9 now? Well, it turns out that we can get global existence with the quantity below 2 pi over 3, but this proof is not going to work unless it's smaller than 2 pi over 9. You're going to see why in a minute. It would be really interesting to work out what happens in this intermediate interval. You have global existence, definitely, but what does the flow do? I personally think my conjecture would be that it's fine, that this is a technical condition and not necessary. So there should be a way to get an estimate like this working without requiring this stronger condition. And also, we've got to keep in mind that this is well below the pi squared that we had before as our kind of goal. Okay. So assuming that we have this at time 0, then we actually get, for the curved diffusion flow, so where f is KSS, we actually get a very strong decay estimate. It's exponentially fast. Okay, so the norm squared of the speed, KSS, is bounded by an exponentially decreasing factor. This is very, very strong, and this is very powerful, and this basically gives us everything. So how does it work? Okay, yes, there exists a delta 0. So how does it work? Well, using methods that we have talked about already, like the commutator, integration by parts, you can find the following equation. A calculation shows ddt of KSS and L2 is equal to, you've got the diffusion term, which is going to have 4 derivatives because it's 2 more and it's a 4th order equation. And then you have some good terms and some bad terms. Now you can write these in many, many equivalent forms because you can integrate by parts and change what they look like. This form I've used in this work because it is amenable to the technique I want to use to estimate the reaction terms, these bad terms that don't have a, well, this bad term especially that doesn't have a sign. This one is a reaction term. Okay. So let's call them names, T1, T2. And I'm going to start with T2. So why not? Start with T2. Basically, we're just going to use our regular tricks, our normal tricks. But there's a few steps, so I'll go through them. We start off with the Hölder inequality. We split this as product of two functions. First, KS4, and then the second, these KSS k squared. We take it out in L2. And we have to be really careful with the powers here. So you see, it's 2, but the power here is 1. And if we make too much of this KS4 over here, we're not going to be able to absorb. So we have to be very careful. We have to be very conservative with our estimates. Okay, now just for clarity, I've written this as the square root of a square, so you can sort of see what's going on inside here. Now the first thing we do is take out the k squared in L infinity. Now because it's a square of a square, it turns into the fourth power. Okay, that's just taking something out in a supremum, it's easy. Now what we do is we apply the Poincare inequality to k. The L infinity version, it's going to give us a constant of 2L over pi, but it's squared, so this would be, okay, this should be 4L squared over pi squared. I'm sure I'll fix it. I will fix it. Okay, and then you've got KSS in L2. And now what we need to do, we need to be very careful because it's very tempting. I'll give you a warning. It's very tempting to use the Wirtinger and Poincare inequalities on this term to turn it into this one. And then you can turn this one into this term by doing the same thing again. But if you do that, you are going to end up with like a lot of powers of L and a cube up here on the power 3. You can't use that. That's not useful because you've got a second power here. You can't go above 2. So you have to be a little bit careful with how you estimate this term. We use an interpolation inequality, which I'm sure I'll explain. Yes. So this fourth power is equal to this integral squared. And now what we do is use the no flux condition, integrate by parts. You end up with this. And now use the Hölder inequality. So this is the most basic kind of interpolation inequality that you can have. And that's what you get. Okay, so going back here, we substitute that in. I hope I fix that constant sometime soon. Oh, and also I've put a 2 here. That 2 should not be there. Hopefully that'll get fixed soon. And yeah, you end up with that. And now the 2 that you get on the KSS from here combines with this 2 and gives you a 4. And now you can sort of see again if you just use Poincare Wirtinger, you're going to end up with too many powers of this again. So you have to be careful. What we're going to do is again interpolate. So you've got this fourth power, that's the integral squared. You do integration by parts, you differentiate the boundary conditions in time, you use the Hölder inequality, and you are ending up with this. So now substituting that in here. Okay, I fixed that power. Good job, Glenn. Substituting that in there. I still haven't fixed up this 2L over pi. Anyway, I'll fix it up in a second. You get, okay, we've got another power of the curvature in L2, which is fine. Now I fixed it. 4L squared over pi squared. 4L squared over pi squared. Good. 4L squared over pi squared. And then you have KS4, but now the power is not 4, the power is 2. Good, and this is where I was up to. So, where's my cursor? Oh, I had the pen in the wrong way. Okay, so now we take the square root, and now you see the power is going to be exactly 2. And so we have to be a little bit careful here because arithmetic is difficult. 4 times this, but this square root. So 4 times 2 is 8. That is equal 8 over pi. And then I'm just going to write this as L, because it's square root, right? So L K in L2 squared. Okay, and then of course there's this factor, which I can just cheat. Stick him there. And don't forget the power. Okay, so that's the first term. Well, it's actually T2, but anyway, that's the first term. And then for the second term, we do something similar. So let's sort of keep these guys in our back pocket and put it up here. All right, now for T1, sorry. Let's have a look at what T1 is. It's KSS in L2. And what we want to do, I think, what we want to do is take this KS out in L infinity. I changed the pen icon and now I keep writing the wrong thing. The human mind, or at least my mind, it's very sensitive to change. All right. Now this is 0 on the boundary, so I'm using the Wirtinger inequality, which is going to be L over pi. And now I actually get back a copy of this, so I end up with KSS to 4. And if you look at actually just conveniently this estimate here, interpolation, I'm just going to apply that straight up, and I'm going to get L over pi, and then I've got, oh, not L over pi. I'm going to take the L down because I want the L to be connected to this L2 norm of the curvature because that's our quantity. And then I've got this KS4. Okay. So now putting everything together, we're going to get our estimate. And it's actually not going to be that bad. So ddt of KSS to 2 is going to be the smaller than or equal to minus, and then you've got the 2 from the good term, minus. And now both of these estimates have a common factor of our quantity, so I'm just going to take that up front. Okay, and now for T1, the coefficient is 1 over pi. And for T2, the coefficient is 8 over pi. So it's 1 over pi plus 8 over pi. I think we can work that out. 9 over pi. Okay, and then of course you've got the L2 norm of KS4. Okay, so now according to our assumption, this is smaller than 2 pi over 9, strictly. It's important that it's strict. So that means that it's preserved by our earlier argument, but it also means that this is less than or equal to minus some delta 0. And then you've got this term, but again, we can play our usual tricks and estimate this using Poincaré and Wirtinger, and we will actually end up back with KSS. And this constant is going to depend a bit on the length, but those are uniformly estimated, so no problem. Now, what we've got is ddt of some quantity is smaller than or equal to minus a constant times that quantity. That gives us exponential decay as required. Awesome. So that's the end of that. Now we've got exponential decay. It's a short hop, skip, and a jump to the end. And so I'm going to actually do it. So convergence. So first, because we have KSS bounded by, so if we have exponential decay for this quantity, that means that we actually have exponential decay for everything. Why? And even in L infinity, it doesn't really, yeah, it's everything. So this is going to be CE, to the minus some other constant. but it doesn't depend on L actually. So this delta 1 does not depend on L, but the C down here does depend on L. It's not important. The reason why this is true is interpolation. So we've got all derivatives of curvature, including the curvature itself, bounded by what we had before, and now we have one of them decaying exponentially fast. You can always move up and down the ladder of derivatives of curvature to interpolate. So basically, you start off with this quantity, and then you estimate it by one more derivative in L2, and then you integrate by parts to move the derivatives around until you end up with one of these. Use the Hölder inequality, and then you'll get your estimate. So that's great. So they're all decaying. And now, if you remember, there was another problem, which was to actually bound the position vector uniformly. And for this, we go back to the flow equation. So our flow equation is something on the derivative, the time derivative of gamma, and something like this. And now what we've got is that this quantity is actually decaying exponentially fast because in the case of curved diffusion flow, it is KSS. In the case of the free elastic flow, there's a cubic curvature term as well, but once we get our first step done for the free elastic flow, we're going to have that decaying exponentially fast as well. So this is decaying exponentially fast. Let's call it delta 2. All of these are independent universal constants. Then what it means is that we can integrate the flow equation and get that gamma at any space point and any time point, let's call it Ti, minus gamma at any space point and another time point, Tj, is bounded by. Okay, now you integrate the right-hand side, some constant, integral Ti, Tj. You can assume that Ti is less than Tj. And then you have this f in L infinity dt. And now you can just plug in this exponential factor, and you're going to get, because, I mean, you can just integrate it. You can just integrate this guy. You're going to get at least something that is smaller than or equal to c e to the minus some constant, let's say delta 2 Ti. Okay, so in particular, if you take these times sufficiently large, this distance becomes very small. And so what this means is that for any subsequence, gamma Ti is Cauchy. It's a Cauchy sequence, and from a course in mathematical analysis, hopefully you've got one of those under your belt. If you don't, that's okay, but just believe me. That means that there is a convergent subsequence for gamma, and that means we can extract a limit. In C0, so we can extract a limit for the curvature, for the position vector itself. We get a uniform estimate, of course, as well. And that means once we have a limit, the subsequence is arbitrary, the whole sequence is converging, and all the derivatives are converging as well because of our estimates here. So, and it's exponentially fast because that's the rate. So that's done. I'll just write convergence in C infinity to a line. I'll do an exclamation mark. Why not? We're excited by finishing our result. Okay. So that's it from me for this one. Next time we're going to do the free elastic flow, and if I have one more, it'll just be some simple questions. And that's it. Thank you for your attention, and I'll see you in the next one. Peace.